Alrighty, my name is Brian Shoemaker, and I am going to present my banker's algorithm implementation. Just to show you, I have already built it up here so it's ready to go. This is a resource allocation and deadlock avoidance algorithm that's used in operating systems, and it determines whether granting a resource request will leave the system in a safe state or could potentially lead to a deadlock. I will walk you through the key components of my implementation. So let's go to my class here. The purpose of the banker's algorithm, as you see in my notes, it maintains a system state using 4 keys data structure. The available tracks currently available resources, maximum store maximum resource claims, allocation tracks currently allocated sources, and then the need obviously calculates the remaining resources needs is the maximum minus the allocation. So that is safe here. So method for set total resources. Purpose is set the total number of units for each resource type. My parameters vector containing total units for each measuring type. Initially, all resources are available, so none are allocated. Alrighty here. So going a little bit further down, my display state. Purpose of the display state is display the current system state in a formatted table. This shows available resources, and for each process, it also shows the allocation, the maximum, and the need. This will help us visualize the current state of the system and is useful for debugging and demonstration purposes. Alright, so my is safe state. This is the main part here. My algorithm steps initialize the work. Available and finish is false for all I. Find a process I such that A, finish I is false, or B, need I is less than or equal to work. If found, it stimulates the process completion. Work is work plus allocation I. Finish I is true. Repeat step 2 until all processes finish or no process can be found. If all processes finish, it is safe. Parameters for my safe sequence. Output parameter that stores the safe sequence if found, and it returns true if the safe sequence exists. It's false if no sequence exists. Alright, let's go into my algorithm here. I have built it to have some default examples here, so I'm going to choose choice 2. Alright, as you can see here, using default example, we loaded 5 processes, 3 resources. So the available resources for my current system state is R0 is 10, R1 is 5, R2 is 7. Look down and see the process here. For P0, you see your allocations. P1, allocations. These are all 0 when they first start. Maximum 735 for P0, P1, 322, P3, 222, P4, 433. Go here, deadlock prevention demonstration, yes. And then we can also see here, interactive session, the available commands. It's request resources. If I wanted to release my resources. State, display current state. So I am going to go ahead and say request. I did that wrong, sorry. Alright, well, I think I'm just goofing that up there. I'm trying to read through my notes here and I got a little lost. right, so we're gonna try this again. Request 01. There we go. Now I did that right. Request 101 is granted. Request was approved. Safe sequence P1 to P2 to P3, P4, then back to P0. Now let's see the state of that. Again, comes back to our original state. And then I can say exit. It'll exit through. Sorry for the pause in that. I lost my place in my notes. As you can see, all of this runs. I have extensive notes further through also, so anyone can read and see what is going on. It probably has a little too many notes, but I would rather know what I'm working with and delete the comments later than be blind. So without further ado, that's the end of my video, and I hope you enjoyed.